The afternoon session of the EPICO. We have two talks now. The first one by Keisuke Shibuya from the AIST in Tsukuba. His talk is phase control of bistable metal-insulator states in vanadium dioxide.
Thank you very much. My name is Keisuke Shibuya from AIST. So first of all, I'd like to thank organizers for giving me a chance to attend such a nice meeting. And actually, I used to work on the resistive switching when I was in Zurich, but in these couple of years, I'm a little away from the switching behavior and investigating more fundamental issues. So today I'd like to talk on phase control of vanadium dioxide. Recently, I moved from Riken to AIST. Both are national institutes in Japan. But all activities I will show you today is done in this previous institute. Okay, so let me explain the location of this two institute. And this is here is Tokyo. This is around Tokyo area. And airport is here. And Riken is the Institute of Physical Chemical Research and located at the edge of Tokyo Prefecture, about 10 kilometers away from the city center. And the AIST is in Tsukuba City, and it's about 60 kilometers away. And it takes about 1 hour by train or car. So let me start from the background of vanadium dioxide. And it shows our insulator metal transition accompanied with a structure change from high temperature rutile to low temperature monoclinic phases. And vanadium dimerization occurs in the latter form, which opens a gap at Fermi level. And most spectacular feature of this material is that transition temperature is above room temperature. And in the Roti curve, it shows a sharp jump at the transition temperature in non-doped case. And it is possible to stabilize a metallic state by chemical substitution. This I will mention later, but it is possible to stabilize insulating and metallic phase even at room temperature. So, and as discussed in the morning session, one of the serious problems in the arena is this SNI current, undesirable current through these cells. And in order to avoid this problem, so recently, VO2 has been investigated as a blocking layer for sector devices. And in this paper, they fabricated this kind of hybrid structure composed of TiO2 and VO2. As you know, TiO2 shows switching behavior, bipolar switching, as you can see here. And VO2 shows this kind of ID curve. Insulator to metal transition by applying voltage. By combining these two, so the memory operation become very stable. So the advantage of this structure is not is that without inserting a metal layer, they can create this kind of structure. So in addition to the electronic properties, VO2 has been investigated for other applications, such as a smart window or photo switches. Here, the phase is controlled by the temperature, and in this case, zero heating. And these properties is a so-called samchromic properties. And here, the phase is controlled by the heat or thermal effect. And the aim, when we think about the controllability, other fields such as electric or photon pressures are more promising. So the aim of this study is to control the phase of vanadium dioxide by these external fields. So this is the outline of my talk. So first, I'd like to mention the chemical substitution, and next two is these are attempts to control the VO2 phase by structure, and last three are external field induced phase transition. So this is my collaborators. Kawasaki is my supervisor, and Tokura is a group leader in DChem. And these are collaborators. So let me start from chemical substitution. And it is possible to stabilize metallic state by chemical substitution. And tungsten, the substitution of tungsten for vanadium is known to reduce the transition temperature most effectively. The valence state of tungsten is 6+, and such that that of vanadium change from 4+ to 3+. This means that it's electron doping into VO2. We fabricated this vanadium tungsten O2 epitaxial thin film on titanium dioxide 001 substrate by pulsed laser deposition. And as you can see, with increase of tungsten concentration, the transition temperature shifted to the lower monotonically. And eventually metallic ground state was observed between x equals 0.08 and 0.09. And further increase of tungsten concentration emerges another insulating state. Here shows a phase diagram of electron doped VO2. In lower doping region, spin singlet formation is destabilized with electron doping. This is due to the enhancement of electron kinetic energy. And in higher doping region, strong electron correlation of vanadium 3+ band likely to contribute the formation of this new insulating state. Presumably this is a motor insulator with antiferromagnetic ground state.
So how can it be a multi-solar fractional doping? Usually multi-solar is an integer doping.
Pardon?
Multi-solar is normally an integer doping, or not that doping materials. I don't understand how it can be a multi-solar.
Actually, valence state changes from 4+ to 3+. The end, so for example, 0.33, all vanadium becomes 3+. This is in this area, it's a motor insulator, as well known in the V2O3. Anyway, the ground state is an antiferromagnetic insulator. So the point is that the electron doping can control the transition temperature, and the metallic state can be stabilized by chemical substitution. And we also investigated the lattice, charge lattice dynamics by optics for these thin films. And here, optical conductivity for x equals 0.05, and it's monotonically reduced with decreasing temperature. And we can see the spectral weight change from this region to higher energy region, indicating the role of electron correlation. And here we have a composition dependence. The gap of non-doped VO2 once collapsed at the metallic region, and drew the right response was obtained. And further increase of concentration emerges, again open the gap. This is consistent with transport data. And electronic structure is investigated by photoemission spectroscopy. And here, around 5 electron volts, there is a shoulder, mainly contributed from the hybridization between tungsten 5D and oxygen 2p orbitals. This is near EF spectra, and in lower doping region, the typical behavior of the sharp EF around here and sharp spectra around EF and satellite peak about 1.4 electron volt was seen. And in the insulating layer, single peak about 0.8 was seen. This is a typical behavior of high-loss insulator, and that remains dominant in the lower doping region. And in higher doping region, modern behavior was seen, namely the spectral weight change from coherent peak to incoherent peak was observed. So here electron correlation became dominant in the whole concentration region, but the spin highest instability is weakened with electron dropping. So let me move on the second topics, the superlattice structure. 3 years ago, there is a prediction that a half-metallic state with a semi-Dirac point surface has been observed at the TiO2-VO2 interfaces. And as a consequence of quantum confinement of d electron in VO2, collective dimerization is suppressed, suggested to be suppressed, and therefore VO2 remains in metallic state. So this is a prediction. So we constructed this kind of superlattice structure, and actually the similar D1, D0 system has been intensively studied in the perovskite structure, but less in other systems. So another motivation is to investigate interface property in rutile structure. So this is the XRD pattern, and here we fix the layer thickness of TiO2 is fixed at 5 G cell, and that of VO2 is varied. And here is the temperature dependence of lattice constant. And as you can see, the sharp decrease around 300 or 310 Kelvin. This indicates the structured phase transition. And actually, the feature of the dimerization was seen even as the layer thickness of VO2 is 3 unit cell. So this is due to very robust vanadium dimerization even at the interfaces. Actually, nor metallic or neither metallic nor ferromagnetic state was observed, or insulating ground states. So because we haven't observed metallic state in the previous case, so we utilize inherently metallic electron doped VO2 alternatively. So we fabricated this kind of superlattice structure. Here, XRD is much better because both TiO2 and electron doped VO2 has a rutile structure at room temperature. And actually, the non-doped electron doped VO2 single layer shows a metallic ground state. All superlattices, these all superlattices shows insulating ground state. So this is a kind of short summary of these superlattices issues. And transition temperature is plotted as a function of VO2 thickness. This is case of TiO2 non-doped VO2 and TiO2 electron doped VO2. And the transition temperature is almost constant due to the very robust vanadium dimerization. And the effect of electron dropping is weakened, reduced by reducing this film thickness, VO2 layer thickness. And similar behavior was, similar reduction of conductivity was seen in perovskite structure, in this case, strontium vanadate and strontium titanate superlattices. But the sensitivity to the film thickness is more significant in rutile structure. This is due to the very strong electron-lattice interaction in this system. So let me move on to third topics, and this is junction properties. Here we doped niobium to the substrate. So we utilize a conducting substrate. So first, we performed chromium substitution in addition to tungsten doping, tungsten substitution. And this valence state of chromium is 3+, so this acts as a whole doping. And actually, the transition temperatures slightly increase with chromium concentration, and this is consistent with previous report in bulk form. So we fabricate this kind of junction structure, and we measure the capacitance of this junction, and 1 over t squared is plotted as a function of voltage. This is the case of electron doping and hole doping. And as you can see, by electron doping, the built-in potential is decreased, and on the other hand, it's increased in hole doping case. And here, temperature dependence of the built-in potential and nominal donor carrier density are plotted. And this, when BO2 is in metal structure, so we can say this is a simple Schottky junction. But the question is what happens when it go to the insulating state. So the carrier density of BO2 drastically reduced, so we can expect enhancement of the nominal carrier density. That's why the nominal carrier density should be dropped at the transition temperature. But that was not observed in the experimental result. So there's no indication of depression layer in BO2 side. So this is a picture of the band diagram. So depression layer was only observed in TiO2 side. And here, the built-in potential is plotted as a function of valence state, nominal valence state of vanadium. And this dashed line is satisfies this relationship. And this is consistent with perovskite report, perovskite structure with transition metal perovskite structure qualitatively and quantitatively. And deducing from this data, we can make this kind of band diagram. The work function of BO2 is approximately 5 electron volt. And this is consistent with the reported value. And by electron doping, it can be reduced and increased by hole doping. Actually, this work function is one problem. So all metal electrode has a ohmic contact against BO2. Even platinum has an ohmic contact to BO2. So far, we haven't succeeded to make a Schottky junction between the metal electrode and BO2. So from now on, I'd like to talk on the external field-induced phase transition. So the first example is electrical field. So now we know it is possible to stabilize metallic state by electron doping. So we constructed this kind of structure, and by accumulating charge at the interface, we demonstrate localization or delocalization of electron in BO2. So we constructed this kind of structure. As a gate insulator, we utilize ionic liquid, which provides a huge amount of carrier at the interface. And this is the photograph, and we use a conventional photolithography and argon ion bearing etching process. So this is the result. Resistance as a function of temperature at various gate bias. So gate bias is positive. It means the electrons are accumulated at the interface. So by increasing the gate voltage, the transition temperature shifted to the lower, and finally the metallic conduction was obtained at the 0.9 volt. And it is possible to observe the non-volatile action just below the room temperature. And insulating state and metallic state was clearly switched by repeatably. And on-off ratio is approximately 100 here. And we also investigated thickness dependence. And the most important thing is when we plot the conductance and thickness, it shows almost a uniform line. It means that these devices provides a single conductance. This means this phase transition is three-dimensional. And this is completely different from the conventional FET, conventional field effect transistor, which provides only electron accumulation at the interface. This behavior can be explored, examined, explained as follows. And electrostatic charge accumulation drives the all localized electron to motion, and that emerges as three-dimensional conduction. So this is probably due to the very strong electron interaction and electron lattice coupling. So let me move on to X-ray photo-induced phase transition. This is a kind of a photo-induced phase transition. And about 10 years ago, it is reported, Cavalieri reported, and photo-induced phase transition using a single crystal at room temperature. And they irradiated infrared light, and they measured the femtosecond XRD. And this is a low temperature phase, and they clearly see the existence of the rutile phase around 1 picosecond. And unfortunately, this state is relaxed within several nanoseconds. So this is not persistent phase transition. So we observed persistent phase transition at low temperature using X-ray. In this case, we utilize this electron doped DO2, which is very close to the metal insulator boundary. And original state is this gray line, and by irradiation of X-ray, we can observe this blue line. So the conductivity reaches to that of metal BO2. And actually, we utilize this kind of configuration. And because XRD irradiation area is larger than that of bare thin film surface, and X-ray penetration depth is much thicker than that of film thickness, we can discuss the resistivity or conductivity quantitatively. This is the advantage of using this kind of thin film. So we explored the transition dynamics in detail. Here, the experiment at low temperature. The conductivity and volume fraction of metallic phase is plotted as a function of irradiation time. Here, X-ray is intermittently off as indicated this dashed line. Actually, this volume fraction was calculated from this XRD peak. So original shape is this, original line is this insulating phase, but converted to the metallic state by irradiation of X-ray. So when this metallic volume fraction is deduced from this X-ray. And deducing from the metallic volume fraction, we can conclude that one X-ray photon creates a metallic pad with a diameter of approximately 30 nanometers. Namely,
how does it decay with time if you stop the radiation?
It's a constant, no change.
It does not decay.
No decay.
Why is that?
This is because this is persistent phase transition. And of course, at high temperature, we can see the relaxed behavior, but low temperature, no decay. Actually, such a metallic pad is connected to each other, and finally, the metallic state is seen. So actually, the actual dynamics depends on the incident flux density. Here, resistivity and diffraction intensity for the insulating phase is plotted as a function of irradiation time. by increasing photon flux density, the time scale becomes shorter and shorter, as you can see. Actually, this behavior can be scaled by the time integrating photon density. So this means both the conductivity and the metallic volume fraction are determined by the total dose of X-ray photons. And that's a special difference between the conductivity and metallic volume fraction indicating percolation behavior. And when we plot the conductivity and volume fraction, this is fitted by the conventional three-dimensional percolation model. So the last one is pressure induced phase transition. And recently, people make this kind of VO2 nanowire, and they fabricated on the flexible substrate as a pressure sensor, and they observe this kind of behavior by bending the substrate. So actually, it is very important to know the effect or a pressure effect on VO2. That is our motivation. So this is our pressure effect for this electron of VO2. And originally, again, this is the insulating ground state was suppressed, resistivity is suppressed by applying a pressure. And here, we utilize a cubic anvil system in order to apply the hydrostatic pressure. And we measure our sample in this system. And by applying more than 4 gigapascal, we observe the metallic ground state. So we also investigated XRD under high pressure with a combination of diamond cubic anvil cell and the synchrotron X-ray. So the film is patterned like this size and put in the diamond cubic anvil and measure X-ray. And this is this constant versus temperature. And at the ambient pressure, it shows the structure transition and represented by this increase of lattice spacing. And that is not observed in high pressure. So here, the lattice constant of VO2 and TiO2 are plotted. And at ambient pressure, as I told you, it shows structure transition, but that was not observed at high pressure. This means the electron of VO2 has a rutile structure in this temperature region. And we also performed a whole measurement for electron of VO2 thin film. Actually, here I little bit increase the tungsten concentration because here we use piston type cylinder cell. So the maximum pressure is about 2 gigapascal using this system. So this is again the Roti curve under various pressure, and we can see the insulator metal transition by applying pressure. And we measure a Hall effect for these pressures, and the ambient pressure, dimerization occurs. That's why the carrier concentration is dramatically reduced at the transition temperature. Actually, under high pressures, it has a very huge carrier density as well as VO2. This means that this high pressure phase is correlated metal, not diluted semiconductor. So here shows our three-dimensional diagram, temperature and composition and pressure. At the phase boundary, we can clearly observe the pressure-induced insulator metal transition. Actually, the pressure is not sufficient to provide insulator metal transition for non-doped or lightly doped one. So much higher pressure seems to be required for these areas. So let me summarize my talk. And metallic state is stabilized by chemical substitution, and collective dimerization is so robust even at interfaces. And electronic structure, electronic phase of VO2 can be controlled by external fields such as electronic X-ray and high pressure, and so on. And electronic state is closely interrelated with lattice structure change in this system. And the electric field control is most powerful tool for device application. Thank you very much for your attention.
Very impressed with your data, and I will just limit myself to one question because others have questions. In this fascinating electron doping, you said you can go from this VO2, which was band insulator, metal phase, and then the metal-insulator, and then you said that the metal-insulator at low temperature is antiferromagnetically ordered.
We speculate that
yes.
We don't have a direct experiment evidence so far. But
That's what I was asking. So you didn't measure the nail temperature, actually, because I was wondering how the metal-insulator transition is correlated with the onset of magnetic order. Do you have any feeling about that?
So, as I said, we don't have direct evidence so far. Now we are working on neutron diffraction for this system. So soon, we can know the nail temperature for this.
Why don't you just do the cosmic magnetization? Even doing magnetization measurements, one should be able to get the cosmic susceptibility.
Actually, it's difficult to. This is the thin film, so it's almost impossible to measure the antiferromagnetic state in thin film.
So I have a couple questions. So regarding the X-ray data, so how do you know that you are actually not heating the sample with the X-ray?
We estimated this is about 1 Kelvin, something like that. So, but heating effect is almost.
But you assume always that you have an homogeneous distribution. I mean that you don't have a phase coexistence to calculate these numbers. So, but the fact is that you have a mixture of these phases. So how do you do that actually? So from the experiment, how do you know that you are not heating the sample? From the data that you show us, how do you know?
You mean the X-ray induced phase transition?
Yeah. So when you calculate these numbers to know how much you are heating, so you are assuming that the whole film is homogeneous. So you are assuming that the whole vanadium oxide is in an insulating state, right? But that's not the case. You actually show it actually. So you have a mixture of these two. So how do you know actually that the other part of the sample is actually getting hotter with the X-ray than the insulating part?
I don't catch your point, but
well, that's something so we can discuss later about that actually. And I have another question regarding the curve that you show with resistance. So you have a loop.
Yeah.
When you put the gate.
Yeah.
Can you put the picture, please? Exactly. So how come that you have this resistance at 0 voltage? So where is that resistance coming from? So if you go to 0, so you have
here you mean? Or here?
Yeah. So how is that measuring actually? So how are you measuring?
This is the gate voltage. No, not source drain voltage.
Okay, but so, wait.
It's a 3-terminal device.
This is a FET structure.
Yeah, exactly. So
we are applying gate voltage here, and always a very small voltage is applied to the drain.
So you are moving charges between so you create this kind of a channel between the electrodes, and that's why you're measuring?
Yeah.
So how do you know that it's actually increasing into the vanadium oxide? So it can be, so is that a real measurement from the vanadium oxide? It's just because you have a capacitor there and then you're just...
We are measuring the VO2. This is the channel radio. The others are insulator.
Okay.
It comes from the VO2.
Now, my question was just the amount of current you had. Wow. But you said it's a small voltage, right?
Yeah.
Source of drain.
In the source drain? Yeah. So, I don't remember exact number, but in the range of millivolt. Yeah, right.
Any other question?